On today we discuss the greedy method. So what is greedy method? So in greedy method, the main problems are divided into many sub problems. Then the sub problems are solved. And after solving the sub problems, we have to find the optimum solution. So what is the optimum solution? Optimum solution means the best solution. So in greedy method, in final, we find the optimum solution. So there are many components of greedy approach. So a set of candidate, a selection function, a feasibility function, an objective function. In greedy method, I'm saying for an optimization problems, we are given a set of constraints. That means we are given a many values, and then we find out the optimization solution. So for calculating the optimization value, we have to find the feasible solution. So feasible solution means the best possible value. Okay. So for finding the optimal solution, we have to find out the feasible solution. So we attempt to construct an optimal solution in the stages. So each and every stage we make a decision that will be the best and under some constraints at the time. So on that time a decision made each and every stage, and that is not changed in the later stage. Okay. So each decision should assure the feasibility. Feasibility means the best possible value. So here is the greedy algorithm. So in this greedy algorithm, we just define the two variables a and n, and the solution will be defined by the phi, and then we declare the for loop I, the value of I would be 1 to n, and then we use do, and then x equals to select a, and then I'm declaring the if statement, if then statement, and after declaring the if then statement, we find the solution equals to union of solution x, and then we can get the final solution, that is return. So now I'm discussing the fractional knapsack that is solved by the greedy method. So what is fractional knapsack? So suppose I have a bag and the size of the bag would be fixed, and n is the number of elements and m is the weight of the knapsack. Okay. So here in this slide, I'm just showing the input profile vector and input size vector. Okay. Input profile vector is in the range P1 to Pn, and input size vector from between S1 to Sn, and then the output fractional part size of the sack x1 to xn. So Pi is defined by the profit associated with the ith element, and Si is defined by the sack of n elements. So two conditions that are required. So number one, summation n I equals to 1 Sxi less than equals to b. Okay. And the next, summation I equals to 1 Pxi equals to the maximum or the minimum, anything else. So now I'm just discussing the fractional knapsack by the nat chat in a highest profit or lowest profit in profile vector, or largest element or smallest element in the size vector. So assume that the part of first element, x1 part of first element or x2 part of second element, so dot dot xn part of n element is taken. So here is the mathematical formula for calculating the fractional knapsack. So here is the algorithm of fractional knapsack. So what is the time complexity of fractional knapsack? If the elements are sorted, then the time complexity of the fractional knapsack will be big O of n. If not sorted, then big O of n log n. So at first we declared the mn variable. M means the size of the knapsack or weight of the knapsack, or n is the number of element. So I'm declaring the for loop. So the value of I equals to 1 to n do, and then the value of xi is defined by 0. Then I'm just taking the u equals to m, and then another I'm applied the for loop for I equals to 1 to n do. Then we can check the wi greater than u by using the if then statement. If the if it will be possible, then the value of xi equals to 1 or u equals to u minus wi. So the final check would be if I less than equals to the n. That means the value of I less than equals to n. If it will be possible, then xi equals to u by wi. So now we are solving the fractional knapsack problem, the mathematical problem. So here is the question. So in the questions, I'm giving the knapsack, the weight of the knapsack m equals to 9, the total number of elements n equals to 4, and the profits p1 to p4 equals to 4984, and the size s1 to s4 equals to 4341. So in this problem, I'm just at first, what can I do? I'm finding the profit by size, the ratio of the profit or size. So at first I found the ratio between the profit and size, and then I'm applying the formula for the 1 unit of fourth element, 1 unit of second element, then third, and then fourth. The formula of the size will be w1x1, the profit will be p1x1, and in a similar way I'm just finding the whole profit and size from the whole table, and then at last I'm finding the maximum profit by addition of the maximum profit value or the maximum weight value. Then ultimately we can find the maximum value by addition of all the elements of profit and size. So here is the another problem from the like previous one, and this is the programming code of fractional knapsack that I discussed in a laboratory, and here is the output of the fractional knapsack program. So now next topic will be the spanning tree, that is also a greedy method. So at first we have to discuss tree. So what is tree? A connected graph without any cycle is called a tree, and also connected acyclic graph is a tree. So a tree is like a graph, that means a connected graph. So let G equals to V. V means vertices or E means edges. So V an undirected connected graph. A subgraph tree equals to V of E dash of G is a spanning tree of G if and only if T is a tree. So the main point of the spanning tree will be there would be no cycle. Okay. If there will be cycle, then we cannot say a graph that the spanning tree. The main part of the spanning tree or the main property of the spanning tree will be there will be no cycle. Okay. So here is some of the pictures of spanning tree. So here is the minimum cost spanning tree. So here is the edges and the value of the vertices. I'm just finding the spanning tree, the minimum cost of the spanning tree. Okay. So now I'm discussing the Kruskal algorithm, that is also a spanning tree. So here is the Kruskal algorithm. In Kruskal algorithm, I'm just giving the vertices, edges, and the n. Here is the algorithm. The edges are maintained as mean heap, and the next edge can be obtained in the big O of log e time in graph as e edges. Now we are discussing the problem, and that is solved by the Kruskal algorithm. So here is the graph in the question paper. I'm just giving the graph, and that is the whole cycle. The graph would be under in the whole cycle. So what can I do at first? At first, in the Kruskal algorithm, the first step of the Kruskal algorithm would be the edge relaxation. Edge relaxation means A to B, D to E, B to C, C to D, A to E, A to C, or A to D. That means I'm just arranging the value of all the edges in ascending order. Okay. So I'm just finding the edge relaxation, and after completing the edge relaxation, at first I'm adding the edge AB with weight 1 to the MST. Okay. So next D2E, next B2C, but I'm just remembering that there will be no cycle. Okay. If there will be any cycle, then the edges are eliminated from the graph. So in a similar way, I'm just adding the edges and then create a graph, and the graph will not create the cycle. So I'm just saying that is the spanning tree. So now I'm calculating the cost of the minimum spanning tree by addition of all the edges that I have to taken for drawing a graph. So the cost of the minimum spanning tree would be 10. So this is the another problem of Kruskal algorithm, and I'm just solving in a similar way that I discussed in the previous slides. So here is the Kruskal algorithm programming code that I discussed in a laboratory, and here is the output of the Kruskal algorithm. So now I'm discussing the Prim's algorithm. It's another part of the spanning tree. So it's just a simple algorithm like Kruskal. In Prim's algorithm, at first we have to define the graph G, and the vertices and edges of G are VE. So here while loop depends on the number of vertices and also finding the minimum cost that depends on the number of vertices. Prim's algorithm takes big O of n squared time complexity. At first we have to define the T equals to the phi, that means set of the minimum cost edges, and the mean cost will be defined by the 0. B is the arbitrary member of vertices V, and then we have to find the mean cost. Mean cost equals to mean cost plus cost of UV, and then return the T and the mean cost. So here is the problem of Prim's algorithm. The graph is defined in a question. So what can I do at first? In step 1, by algorithm, I'm defining the T equals to 5 and the mean cost equals to 0, B equals to 1, and V minus B equals to 2, 3, 4, 5, 6, 7. I'm taking the B equals to 1, so the 1 eliminate from the 1 is eliminated from V minus B set. Okay. So now after adding the vertex 6, the value of T will become 1, 6, and the value of B will become 1, 6. So now the minimum cost equals to 10. So in similar way, I'm finding the mean cost equals to 10. Now the value of B would be 1 6, V minus B 2 3 4 5 7. Then after adding the vertex 5, then the value of T will become 1 6 or 6 5, and the value of B will become 1 5 6. So the mean cost equals to 10 plus 25 equals to 35. So in a similar way, I'm creating the whole graph, but I'm just remembering that there will be no cycle. Okay. So now I'm doing in every step. So this is the final step, and the graph would be created without cycle. Okay. So the final minimum cost of the spanning tree will be 99. Okay. So now we can calculate the mean cost. The mean cost would be 99. So here is the Prim's algorithm. Here is the some another problem of Prim's algorithm that is solved in a previous way. And this is the programming code of Prim's algorithm that I discussed in a laboratory. And here is the output of the Prim's algorithm. Now I am discussing the job sequencing with deadline algorithm. It is the another approach of greedy method. Here I am given a set of n jobs, and each job I has a deadline di. Okay. So di greater than equals to 0 and the profit pi greater than equals to 0. So I am earning the profit if the job is completed before its deadline. Before its deadline. Okay. So the job is completed if it's processing on a machine for a unique time, then the machine is available for the processing jobs. Only one machine is available for the processing the jobs, and the job is processed at a time on the machine. So one machine is performing the one job in one time. An optimal solution we'll have to find by using this method. Okay. What is the optimal solution? The optimal solution means the best possible value. That is also called the feasible solution with the maximum profit value. Here is the algorithm of job sequencing with deadline algorithm. In next slide, I am discussing the problem of job sequencing with deadline algorithm. So in question, the jobs and the deadlines and the profits are given. There are 6 jobs and there are 6 different values of the 6 jobs, and there are some different profits of the 6 jobs according to the deadline. So at first I am arranging the profits in a descending order. Okay, in step 1. So now I am creating the net chat, and the value of the maximum deadline would be 5. Now we take each job one by one in the order, and I'm putting the job in a net chat. Okay, as per the order. So in step 3, I'm just putting the job 4 between 1 and 2 according to the deadline. Next, I'm putting the job 1 between the 4 to 5 according to the order. So in a similar way, I'm just putting the job in every job on a net chat. If there will be the same value or the same deadline of the job, then how can I do? I'm just putting the empty place on the net chat, and I'm inserting that jobs on the empty place on the net chat. Okay. So in final step, the each and every job are inserted into the net chat, and then we can get the maximum earned profit by addition of all the values. So here will be the final values 990 units. Here is some another problem of job scheduling problem that can I solve in a previous way.